Hi everyone, welcome to my talk. To begin with, I want to thank Professor Lee for organizing the Geometric Analysis Festivals. And today I will talk about a family of integral operators on a ball. So here's some overview. To begin with, I will introduce what is an extension inequality. A very good example is the classic Poisson kernel that can help solve Laplace equation with Dirichlet boundary conditions. And there is a generalization of Poisson kernel to a whole family of integral operators. And then I will introduce my main result and the interpretation of my main result as the Carleman's inequality. In order to introduce the Carleman's inequality, I will talk about the original version of it, and then I will also talk about two other generalizations of it to higher dimensions. Eventually, I'll introduce my own generalization, which is going to be conformally invariant. Lastly, I will talk about the proof of one of the theorems in the limit case. It's actually a theorem in the limit case. And the proof uses the method of moving spheres. So I would talk a little bit about the history of moving sphere methods, and then talk about the sketch of how to apply it to prove uniqueness of the limit case extension inequality. Firstly, let's look at the Laplace equation with Dirichlet boundary conditions in the unit ball, with the unit sphere as the boundary. We all know that we could solve such an equation with the Poisson kernel, which is a function with two variables. And we have the explicit formula over here. Here Cn is a constant that only depends on the dimension n with the Poisson kernel. And if you have a function f tilde which is continuous on the boundary, you can do the integral here to get a function ux, which is a function defined in the interior of the unit ball, and ux will be a solution to the equation over here. Solution. And from another perspective, you can also think of this as defining an extension operator, p of tilde, such that for any f of tilde which is continuous on the boundary, we can define a function which is continuous in the interior of the unit ball. You can think of this function as inside of this set, such that the way to define it is just to use this integral here to define the function that is continuous in the interior. When you do that, you get an extension operator. In the year 2009, Han, Wang, and Yan proved this result about the extension operator in the unit ball. In particular, here Han is Fengbo Han, and Wang is Xiaodong Wang, and Yan is Xiaodong Yan. They proved that for f tilde to be a function that is not necessarily continuous, but think of this as an LP function for a particular p number. And after you do the extension, you get the extended function is going to be in LQ for a particular q. Also, they found the sharp constant for this extension inequality. And they also proved uniqueness of extremal function. They proved that the extremal function has to look like this, where c is a constant and and zeta is an element inside in the interior of the unit ball. There is also a result about Poisson kernel in the upper half space. In particular, I'm using the notation y equals y prime and yn to denote the upper half space. Here y prime is an element in Rn minus 1 and yn is supposed to be greater than 0. The Poisson kernel in the upper half space and in the unit ball are connected by this conformal transformation C. I included the explicit formula for C over here. And C is a conformal transformation between the upper half space and the unit ball. So when you consider the pullback of the Euclidean metric in the unit ball, you actually get a metric that is conformal to the Euclidean metric in the upper half sphere, in the upper half space, where the conformal factor would be denoted like this. It would be used in several places. In particular, I also included the explicit formula for the Poisson kernel in the upper half space. Han, Wang, and Yan also proved similar extension inequalities for the Poisson kernel in the upper half space. They did this work in the year 2008. In the year 2007, Cavaretti and Sylvester studied this generalized family of equations with Dirichlet boundary condition. In particular, there is a parameter alpha here that goes between -1 and 1. They also found the Poisson kernel for this equation. In particular, if you have a function f which is nice on the boundary, then you can do the integration over here to obtain a solution u to the equation over here. In particular, the Poisson kernel actually works for alpha between 2 minus n to 1. And in the case when alpha is between 2 minus n to 0, you can think of it like it's connecting the hyperbolic and Euclidean Laplace equation. Shibing Chen studied this Poisson kernel. In the year 2012, he proved an extension inequality for this particular Poisson kernel with alpha. He studied the Poisson kernel for alpha between 2 minus n to 1, and he proved a similar extension inequality, which is similar to the work of Han, Wang, and Yan. He also identified the sharp constant of this inequality, and he proved uniqueness of extremal functions. He proved that they include constant, and the optimizers are unique up to conformal transformation. Shibing Chen also considered the limit case, which is taking alpha going to 2 minus n. He proved that after taking the limit of the previous inequality, you're going to get an inequality like this. And when he took the limit, function in theta shows up naturally, and its definition is over here. And I need to explain a little bit how he took the limit, which is, I'm going to talk about a sketch of the proof. He considered a function, given a function capital F theta that is nice on the boundary, he considered a corresponding function lowercase f theta, which is going to be 1 plus epsilon times capital F theta. And here epsilon is actually n minus 2 plus alpha over 2, so that when alpha goes to 2 minus n, this is equivalent to epsilon going to 0. And we can consider, he plugged in the lowercase f theta into the previous equation, and this is what he got after plugging in. And when he took the limit of epsilon goes to 0, if we just look at the right hand side, you can see that this part will go to something like exponential of f theta with a constant in front of f theta that becomes the n minus 1 norm over here. The situation on the left hand side is a bit more complicated. In particular, in order to take the limit, we need to find a lower bound for the extension of constant function, something here. And we also need to find an upper bound of this part so that we can take the limit. And these two bounds can be proved using the explicit formula for the Poisson kernel. And I also want to emphasize that here he identified the sharp constant as n, but he did not prove uniqueness of extremal functions. He only proved that any constant is an optimizer, but he did not prove that any optimizer has to be constant up to conformal transformation. So there are some room for improvement in Shibing Chen's work, which will lead to my work. In particular, he did not give the corresponding equation in the unit ball, and also he did not give explicit formula for the Poisson kernel in the unit ball. And he did not give the explicit formula for this function in tilde for n greater than 4. For dimension 4, he actually gave that the function is 1 minus absolute value of x squared over 2. It's a function of x. X is an element in Bn. Oh, it's supposed to be B4. And also he did not prove uniqueness in the limit case inequality. Now I'm ready to talk about my own work. To begin with, I transformed the equation in the upper half space to an equation in the unit ball. I defined the operator L in the unit ball with the explicit formula over here, and I proved that for any u that is C2 in the upper half space, if I define u tilde in this way, which is going to be a function in the unit ball, then the result is u satisfy the equation in the upper half space if and only if u tilde satisfy the equation in the unit ball. And then I transformed the Poisson kernel in the upper half space to a function in the unit ball, which has the explicit formula over here. And I proved that this Poisson kernel can help us solve the equation u tilde equals 0 in Bn, and also u tilde equals f on Sn minus 1. And the proof is similar to the classical result for the Poisson kernel for Laplace equation. And then I considered the extension inequality with alpha, with the extension operator P alpha defined with the explicit formula over here to begin with, which is consider a continuous function on the boundary to begin with, and then extend it to a function that is continuous in the interior of the unit ball. And then I proved the theorem over here, which is similar to Shibing Chen's work, to theorem 1 in Shibing Chen's work. And I used a different method to prove this theorem, and also I did not prove uniqueness in this theorem since Shibing Chen already did that and I don't have a better way to prove it. I also considered the limit case, taking limit as alpha goes to 2 minus n, and I proved the theorem over here, which is similar to Shibing Chen's work and similar to his theorem 2. The theorem that I proved says that for any function that is L infinity on the boundary, if you do the hyperbolic harmonic extension to get a function that in the interior of the unit ball, then you actually have the exponential inequality like this, where again the function in tilde shows up naturally when we take the limit as alpha goes to 2 minus n. And what's good here is that I found the explicit formula for the function in tilde when n is even. So only when n is even. And I am actually not the first one to identify it. It's already been found by Yang in his 2019 paper. It's in arXiv 1901.03945, and in particular it's the formula 3.35. And so later I also learned that if you consider the conformal metric G star equals e to the 2 times I n tilde x dx squared, where this is the Euclidean metric, then the metric G star actually has a name attached to it. It's called the Fefferman-Graham metric. I learned about this metric from the work of Jeffrey Case and Alice Chen, and also the work of Antonio Arce and Alice Chen. So now, if you think of e to the I n tilde as the conformal factor of this conformal metric, then you can actually think of this part as the norm of just the exponential of the p to the 2 minus n tilde f tilde, but measured using the Fefferman-Graham metric. And also you can interpret the sharp constant as the isoperimetric ratio of the Fefferman-Graham metric. I want to talk a little bit more about how I handle the function I n tilde. And to begin with, I proved an inductive relation that concerns all I n tilde. So this works for both when n is even and n is odd. In the case when n is even, this gives the explicit formula. When n is even. Since the case when n is even is easier, because I of 2 of r is actually 0, and I of 4 of r is actually 1 minus r squared over 2. Yes, and since I n tilde is radially symmetric, so I sometimes think of it as a function that only depends on r. The case when n is odd is more complicated, but we can still find that I3 tilde of r is going to be natural log 4 plus 1 minus r squared natural log 1 minus r minus 1 plus r squared natural log of 1 plus r divided by 2r. So if you want to know the function in any odd dimension, you can actually find it, but I don't have a general formula for it. But in the case when n is odd, I can actually just use this inductive relation to obtain a lot of useful information about a function I n tilde. From the inductive relation about I n tilde, we can actually obtain a lot of information about a function. To begin with, I n tilde adding a function natural log of something is going to be 0. Here I think of x as an element in Bn such that x equals x prime and xn. And xn will be between -1 and 1. And I can also obtain important boundary conditions about I n tilde. In particular, it equals 0 on the boundary, and this too. Using the inductive relation about the function I n tilde, and also the information I obtained from the inductive relation, I can prove uniqueness of the limit case inequality. I considered the variational problem, and then get the corresponding Euler-Lagrange equation looking like this. Notice that the function in tilde shows up in the Euler-Lagrange equation, so the information about in tilde was very important for proving uniqueness. I proved the following theorem, which is saying that for any f tilde that is L infinity on the boundary, if it is a solution to the Euler-Lagrange equation, then it has to look like this. Here, zeta is any point in the interior of the unit ball, but Cn has to be a fixed constant because I need to fix the norm on the boundary to get the Euler-Lagrange equation. And the proof here uses the moving sphere method. And I will talk about the proof at the end of the talk. Before I talk about the proof of the uniqueness in the limit case inequality, I want to talk about the interpretation of the limit case inequality as Carleman's inequality in higher dimensions. In dimension 2, Carleman proved the following inequality, which concerns a function u that is harmonic in the interior of the unit ball, and also it is smooth up to the boundary. Then we can have the exponential inequality. Here there's supposed to be 1/2. And he also identified all the extremal functions, saying that equality holds if and only if u is a constant or u is supposed to be a particular form like this. And what's good about this is that this inequality also works for subharmonic function and that it is conformally invariant. There has been several generalizations of Carleman's inequality to higher dimensions. Han, Wang, and Yan proved one version of the generalization in the year 2009. They claim that for any function that is L infinity on the boundary, if you consider the harmonic extension of the function to the interior of the unit ball, then you can have the exponential inequality. Where they also identified all the extremal functions. They proved that equality holds if and only if f tilde is a constant. And as you can expect, this will work for a subharmonic function as well. But since equality only holds when f tilde is constant, so this is not going to be conformally invariant. Shibing Chen also offered another generalization of Carleman's inequality in 4-dimensional unit ball, so that only works in B4, and it concerns functions such that Laplace square of u is less than or equal to 0. Here, Laplace square of u is the Euclidean Laplacian acting on u twice, and also negative of the normal derivative of the function is supposed to be less than or equal to 1. He obtained the exponential inequality like this, but he did not obtain uniqueness for this inequality. He only proved that the equality will hold when u is a solution to the equation over here. In particular, u is supposed to be biharmonic in the interior, and also u equals 0 on the boundary, and the normal derivative is -1 on the boundary. So the issue with this generalization is that there is no uniqueness, and also it is not likely going to work for higher dimensional generalization, just because in higher dimensional unit ball we will have to consider higher order derivative as boundary conditions. For example, if u equals f on the boundary, then we may have Laplace of Sn minus 1 of f kind of boundary conditions. Here this is the Laplacian in the unit sphere with the standard metric. And those boundary conditions, we will not be able to compare them easily. But this generalization is conformally invariant. I'll talk more about this when I talk about my own generalization of it. And here is my version of the generalization of Carleman's inequality. In particular, I want to say that the limit case inequality is actually a generalization of Carleman's inequality in any dimension greater than or equal to 2. I emphasize that n is greater than or equal to 3 here, but it also works in dimension 2. Since I have uniqueness of the limit case inequality, I also have uniqueness here. I know that all the extremal functions must look like this, and since here it concerns the hyperbolic harmonic extension of functions, and in hyperbolic space you still have maximum principle, so this inequality will also work for hyperbolic subharmonic function, which is functions such that you use the hyperbolic Laplacian to act on it, you get less than or equal to 0. And also this inequality will be conformally invariant, in the sense that if you consider any phi, which is a conformal transformation from the unit ball to itself, and if you look at originally you look at a function f tilde, now you define a new function f tilde phi, which is f composite with phi plus natural log of the conformal factor of phi. And then if you plug in f tilde into the inequality, then on the right hand side you're going to get that this is going to be the same norm as e to the f tilde phi. And on the left hand side, things are going to be a little bit more complicated, but using the transformation here, you can also show that this would be the same norm as e to the in tilde plus p2 minus n tilde f tilde phi. Yep, and from this you could see that it's the inequality is going to be conformally invariant. At this point, I want to explain a little bit the relation between hyperbolic harmonic function and polyharmonic function in the case when n is even. As you may notice that Shibing-Chen's work concerns biharmonic function in 4-dimensional unit ball, and my work concerns hyperbolic harmonic functions in any dimensional unit ball. So here, by polyharmonic, I mean in a unit ball Bn where n is even, just apply the Euclidean Laplacian n over 2 times to a function u, you get 0. So this is what I mean by polyharmonic. And the first relation is that if a function is hyperbolic harmonic, then it is polyharmonic, which is over here. And the way to see this is if you define rho to be 1 minus x squared over 2, and then if you write out the hyperbolic Laplacian in coordinate system, this is what you're going to get. And if you keep applying Laplacian to both sides, apply it again and apply it again here, and then you apply it k times, you arrive at this inductive relation over here. Now if you apply exactly n over 2 times, these two terms will just equal 0, so that equals 0, so that you get 0. And that's a proof for hyperbolic harmonic functions are polyharmonic functions. And the other way around is a little bit more complicated, just because for polyharmonic functions it has to satisfy a lot of boundary conditions. So a polyharmonic function is hyperbolic harmonic only when the boundary conditions is right. Here I wrote a non-example, which is the function in tilde. You could calculate to see that it is actually polyharmonic, but it is not hyperbolic harmonic, just because the boundary conditions are very off. In tilde x equals 0 for x is on the boundary.